All right. Hello and welcome to Simply Programming. Today we're going to talk about recursive functions and recursive data structures. That is something some people think recursion in programming is something complicated or something, but really it's not. It's really a very, very simple concept of functions calling themselves and what you can do with it. So we get starting with a simple. Let's start with a simple math example. Like there is the factorial function. It can be used in probability mathematics. But the idea is that if you have factorial of a number, like 5 here, for example, you just take the number 5 times 4 times 3 times 2 times 1. It's usually it's used for if you want to count the number of ways you can order a number of items. Like for example, you have 3 people, they can be arranged in different ways. Then it's usually like 3 factorial is the number of ways they can be arranged. So this is the number of ways you can arrange 5 things. But so this is an example of what you might want to compute in a program. 5 factorial. And the definition is just like this. Like if it's by definition factorial of 0 is just 1. And also any other number, n is the number itself times factorial for n minus 1 here. So that's the mathematical definition. So it's from this definition already. You can kind of guess how that would translate to a program. So let's go to CodePen here and start doing something. There we have a new. So if you want to program factorial here, this is JavaScript again. It's very similar in other programming languages. I'm just using JavaScript for convenience. So and also remember, JavaScript is one of the most common languages in the world because all web browsers in the world know JavaScript. So it's a great language to learn also. All right, so let's start here. Let's define factorial as a function here. Okay. And then we can basically, based on the math definition, if n triple equals 0, then we can return 1. Else, need a space in there for beauty, and then else return. And now we can do the okay. Now we can do the recursive call here of our recursive function. So we time n times factorial n minus 1. And that's about it actually. It's just as simple as that. So what we have here is actually a function factorial, and if we search for factorial, we can see that the function factorial just calls itself with n minus 1. So if we run this, let's see if it works. Factorial of 5. Factorial of 5, and then let's run this and see what happens. We need to get the console up here. Sorry, I forgot. We need to console log our answer also, so we can see anything. Yeah, 120, and that's what you get if you put this in a calculator. So that's really recursive functions are really simple to understand and use. But what are they used for? Like this factorial here could have been done with a while loop instead. You could have just used a while loop to subtract 1 from a counter and then multiply them all into a result. Would be fine also. But where recursive functions really shine, when they start to become really useful, is when we do what we call recursive data structures. And if you have played with Lego, you kind of already would have an understanding of what a recursive structure really is. If you think of it, a Lego piece is like, it has an interface on the top and it has the interface on the bottom. And if you stack a pile of Legos, the top interface is always the same and the bottom interface is always the same also. So you can connect them however you want. And that's a kind of the idea with recursive data structures. And I mentioned trees here also, because what is a tree in data in computer science? Well, this is a tree. Assume you have a tree structure. Usually, when you see them outside when you walk outside and you see trees, they're usually draw the opposite way around. They branch out towards the sky. But when computer scientists draw trees, we usually draw them the opposite way around. So you have they branch out downwards, and you have the root at the top. So that's just a convention. And in here I just have an example of a gem tree. It's a tree that has gems on the nodes here. You can see we have 1 here, 2 here, 12, 4. And this is a kind of, in computer science you often have these kind of data structures. It could be assemblies or something. And now it's not seen completely here. It's out of, okay, let's try again. So here and to the right you can see what we say the JSON representation of this tree. Instead of drawing it as boxes with arrows between, you can have like parentheses, and what you see here is we have the constant, a gem tree, and we have a parenthesis. We have gems on the first level here. We have a left and we have a right, and on the left branch we have the gem, the branch here, the node here that has 12 gems that correspond to this, and so on and so on. So this is, when you have a tree structure, you can convert it into a JSON object also, and a JSON object. So we can just grab this here and oh no, we can just grab this here and put it in our program. This tree here. Okay, let's go to the code again. So we have we have the gem tree here. So let's just print that out and see what happens. We can comment these guys out also, so we don't need them anymore. Let's see if that was correct. All right, yeah, it would have said, if there was some syntax error, it would have complained. So now we have a tree structure here. What about if we want to collect all the gems in this tree structure and sum them up? We want to know the sum of all the gems. We have 23 here, 12, 1, 2, 4, etc. How to sum them up? Yeah. What you can do now is use a recursive function, of course. And recursive functions goes very well hand in hand with the recursive data structure. So we can have a function here that says count gems. Function count gems. Gem. It takes a gem tree as an input, and we want a result. Now we can think a little bit ahead here. So if the gem tree is null, typically the gem tree wouldn't be null, but what if it's a null gem tree, what would we return then? Then we would return 0, of course. Space in there. And otherwise, then what would we do? Now we can look at this structure here, just like with the Lego. They have the same pattern on each level. So each node in this tree has a gems, it has a left, and it has a right. So we can, by using this structure, we can treat all the gem trees we can use the same function for all levels here. So what we do is we return gems plus, and then we can left, start with left. Now there's some line breaks here. So what we did here is just count the gems at the current level and then add all the gems in the left subtree and then add all the gems of the right subtree. And now let's see if that works here. Console log, count gems, and then what was the name? Our gem tree here is called gem tree. Copy paste is always, when you do programming, I often copy paste things because then you know you don't misspell anything and such. So that's a good thing, good habit. Sometimes you write it, but sometimes you copy it. Okay, so let's run this and see if it works. Let's clear that. That one can still be. Okay, let's run. All right, 42, and it says the sum was, so let's see that. Okay, 23, 35, 36, 38, 42. So yeah, that's correct. So now we summed up all of the gems in this tree. So that's that. That's basically it. How you usually use recursive function. It's not very difficult. If you have a tree structure, you want to sum things up in the tree structure, or maybe you want to print out all the items in the tree structure, or you want to do something else. You usually have a recursive function that goes down in this recursive structure. So yeah, that's it. What we could do now is we could create a little bit more interesting example that is a little bit more close to how you would see this in production, because in production, when you work on some program on for a company, etc., they don't like that all this. The structure of this data here is not very typed. It's not very strictly typed. You can add things here, and it wouldn't complain. So that's why we usually use classes and TypeScript, etc. So and also you would also use instead of having loose functions like this that count things, you usually have methods. We have classes and methods. So as a last example, we can just show how you would use this in a more real scenario. Or maybe sometimes you would actually use this, but typically more real scenario. And then I thought about how about if you have a factory and you have assemblies and you have an assembly has a name and it has name. Let's start with that. And also an assembly maybe has a weight, like a sub-assembly in a factory, like you assemble like an engine or a tire, and then you put all the pieces together in the end. And that can be often very described with a tree structure, just like the one we had here with the gem tree. So we have get okay. So get weight here, but that is, we have an abstract assembly. We don't know, we have no weight on this yet. So we just do like this. In some programming languages, you would create an abstract interface out of this instead of having a class. But having a class is typically you can typically do very similar thing with classes. The only thing, like in Java, you can do multiple inheritance with interfaces that you can't do with classes. But in many cases, an abstract class or even a class that throws these kind of things would do the same thing. So we have an abstract assembly, and then we have we have a real assembly here that is that takes a name, and it takes a parts also, and that name, and then we call the super constructor with a name, and then we assign parts on this one. And now we can implement get weight. And how we should implement that, we should do like, we start with an initializing variable, then we can do let's iterate over all the parts in our and for each part we add the weight. And we also use get weight to get the, and note here that the part can be a primitive part, or it can be another assembly. And also we need a way to one primitive part, we call it primitive because it doesn't have any children. That also has a name, and then we already assign a weight here, so we call super, and we call and the get weight for that one. Now let's copy paste that one for do it fast. Remove the content, and then we do it like return is. So a primitive part just has a name and a weight. It doesn't have any subcomponents. And this assembly here has parts, but it doesn't have any weight of its own, but it sums up all the parts. So now we have that. What we can do now is we can create a car here. New and it's called a car, and it has a list of parts in it. So then we can create a new, an it can contain an engine, and the engine could consist out of a new, for example, an engine block that weighs 20 kilos, for example. A piston set that weighs 5 kilos maybe. And it can have a crankshaft also. That is maybe 2 kilograms. So that now we have the engine assembly, and then we can create another, maybe we do more just parts the rest. So we have a part, the chassis is a part, maybe it's maybe 200 kilogram, and we have a interior 100 kilogram. So now we have the car. So now we've also done a kind of recursive function, but it's actually more like a recursive method on this class here, abstract assembly. So we have the recursive thing we have is the get weight here. If we search for that one so we can highlight it, you can see here we have get weight, and for an assembly get weight calls itself get weight for the part. And we have all these, you can say that if we consider like the Lego analogy here, in this case we have Lego parts that are different. Like we have this abstract assembly defines the interfaces of the Lego part, and then we have two different kinds of Lego parts here. The assembly that contains children, and then we have the part here that is just has a weight and a name. So by that, okay, then we can now we should be able to sum up all the weight of this car we have created here. So we can take car, we get weight, and now let's see if we have any bugs or if it works. Let's first start by let's commenting out the geometry stuff here. Like that, and then we start afresh, clear, and then we run it, see if there's any bugs. Super keyword unexpected here. Okay, I think it's about I forgot to this is the problem. I forgot to extend this class. So that means this assembly inherits from this one. So everything that this class has, assembly class will also have. So now let's try it again. All right, undefined. This is usually a sign that you forgot to return things somewhere. So get weight, yeah, return weight. Oh yeah, here we forgot. No, yeah, here we forgot. We calculate the weight, but we forget to return it. So let's run again. 327. So yeah, that seems reasonable. Yeah, 27. So that's the total weight of this car assembly. So that's a more realistic way that you will usually see recursive functions in the wild, so to say. Yeah, and that's basically it. There's not so much more to it. Functions calling themselves, data structures that implement the common interface so you can put them in a recursive structure, and basically that's it. So thanks for watching. Don't forget to leave a like and subscribe, and that's it for today. See you. Bye bye.